All right, this problem is looking at an electrolysis cell. I'm trying to figure out what is going to be the product at the anode. So I always like to write myself a very important reminder, and that reminder is as follows. Electrons always travel in alphabetical order. That is, they always travel from A to C, which means the anode is always where oxidation takes place, and the cathode is always where reduction takes place. If you keep that in mind, these problems become a snap. So, this is a relatively simple electrolysis cell. Usually we have some salts that we have to consider, but this one only has water in it, evidently. So, what we're going to do is look at the oxidation potential of water. So water, H2O liquid, can be oxidized. And the oxidation reaction that we use for water forms O2 gas, 4H plus, and releases 4 electrons, and this comes with a price tag of negative 1.23 volts. Now, you might ask yourself, why do we use this particular oxidation of water? Well, if you consider the other potential reaction, the other one that involves water would be negative 1.776 volts. That's far less favorable than negative 1.23. This takes a lot less work. This is going to be a lot easier to accomplish. So the elemental product is going to be our oxygen gas. And that's going to be our answer. In this problem, we're trying to figure out the relative molar solubilities of these sparingly soluble salts. Now, it can be tempting to try to base your answer solely off of the Ksp, but we'll see that that is a bad idea. So, you can't go wrong with an ICE table. So let's go through each of these. For the first one, now we're given a Ksp, and remember, Ksp reactions are breaking a salt apart. So with Ksp, we're breaking our salt apart. So let's consider what the reaction would be for iron hydroxide. We have FeOH2, solid. It'll associate into iron 2 plus and 2 hydroxides. So let's see how this is different from reaction 2. Reaction 2, notice how when this salt associates, the barium sulfate would turn into barium 2 plus and sulfate. So the first salt turns into 3 ions, the second salt turns into 2 ions. It turns out that has a profound impact on the algebra involved. So don't take my word for it, take algebra's word for it. You can't go wrong with an ICE table. So if we don't care, this is 0 and this is 0. Minus x, classic, plus x, plus 2x, on account of the stoichiometric coefficient. We don't care, minus x is we don't care, 0 plus x is x, and 0 plus 2x is 2x. Cool. Now when we write out the equilibrium expression, Ksp is equal to the iron 2 plus concentration times the hydroxide concentration squared. So when we solve for x, we plug in our Ksp value, 7.9 times 10 to the negative 16th is equal to, and the iron 2 plus concentration is x, the hydroxide is 2x. So just remember that we have to square both the x and the 2x. So 2x squared is equal to 4x squared, but that times x is equal to 4x cubed. Divide both sides by 4, and we get we get 1.975 times 10 to the negative 16th is equal to x cubed. Then take the cubic root of both sides to get that x is equal to 5.8 times 10 to the negative 6th. And remember, x represents the molar solubility. So if you solve for x and rank them in order, you can't go wrong. Now we'll do the same thing for the second salt. Barium sulfate will turn into these 2 ions. So we start with we don't care, 0 and 0. Minus x plus x plus x. We don't care, 0 plus x is x, and 0 plus x is x. Now, if we look at the equilibrium expression, Ksp is equal to the barium 2 plus concentration times the sulfate. I probably should have planned this a little bit better in terms of space. Anyway, so barium 2 plus is X. Sulfate is X. X times X is X squared. So using that information, we can plug them into our equilibrium expression. So 1.1 times 10 to the negative 10th is our Ksp. And that's going to be equal to X squared. Take the square root of both sides, and we'll get that X is equal to 1.0 times 10 to the negative 5th. We are so close to being done. We just have one more left to go. And I hope that you'll see, when we look at this last equation, the Ksp of silver carbonate, Ag2CO3, is smaller than the Ksp for barium sulfate. But does that mean it has less molar solubility? Well, let's see. Spoiler alert, it won't. So for salt 3, we have Ag2CO3. It breaks apart into 2 silvers and carbonate. So we'll do our ICE table. Pretty classic. We don't care. 0 and 0 minus X plus X, actually plus 2X and plus X. And we get X and 2X, and we don't care. So when we plug everything into our Ksp expression, we have Ag plus squared times the carbonate concentration. So when we plug in everything, we get 8.1 times 10 to the negative 12, that's the Ksp, is equal to, and again, this is the silver plus concentration is 2x, so we just square both the 2 and the x, so we get 4x squared times x, which is going to give us 4x cubed, so we get 4x cubed. Divide by both sides by 4 and take the cubic root, just like we did with the math up here, and we'll end up getting that x is equal to 1.3 times 10 to the negative 4th. So if we rank these in order, this is actually the most soluble in terms of molar solubility. The least is this one up here. So the order goes 1, then 2, then 3. So note, if you just base it off of KSPs, you will not get the right answer. But if you look at the ICE tables, you cannot go wrong. So taking the extra time is absolutely worth it here, because that showed us that even though this is the smaller KSP, this is still the greater molar solubility. Here we're looking for which of the following metals is easier to oxidize than iron. So iron's oxidation potential, if we're looking at the solid iron, to turn it into iron 2 plus and release 2 electrons, well, this is actually kind of a favorable oxidation half reaction. So this is positive 0.440 volts, and we can get that from looking at our data table. The reduction potential of iron 2 plus to iron solid is negative 0.440 volts, so if we flip that reaction, this is what we get. So that's pretty favorable. Iron tends to rust. We can protect iron by using something that's more inclined to oxidize. This is called cathodic protection or a sacrificial anode. And if we look at the oxidation potentials, the one that's going to be higher than this is aluminum. So aluminum solid going to aluminum 3 plus and 3 electrons, that has an oxidation potential of 1.66 volts. Look at that. Oh, that's really, really favorable. A whole lot more favorable than iron being oxidized. So aluminum is going to be the winner here. All right, in this question, we're trying to figure out what the Ksp of lead hydroxide is. So this is basically going to be a reverse ICE table. What I mean by that is we're trying to find Ksp. Let's think about what that reaction corresponds to. So it's lead hydroxide, PbOH2 solid, turning into Pb2 plus, aqueous, and 2 hydroxides. All right. Now then, usually we use variables in an ICE table, but in this case we don't have to, because we're actually given information about one of the concentrations. We're told that the pH of the solution is 7.49 at 25 degrees Celsius. So we can reason using the fact that pH plus pOH equals 14 at 25 degrees Celsius. If we subtract that pH from both sides, we end up getting the pOH is equal to 6.51, which means if you know the pOH, you can find the hydroxide concentration. So this means the negative log of the hydroxide ion concentration is equal to 6.51. Multiply both sides by -1. When we do, we'll get the log of hydroxide concentration is equal to -6.51. Then do 10 to both powers, and we'll get our hydroxide ion concentration, which is equal to 3.09 times 10 to the -7th. So we can actually fill this in our ICE table. So we're going to take this and we're going to plug it into our equilibrium value of hydroxide. Because we can reason that we're told the saturated solution, saturated means equilibrium. So we can reason that this is going to be the concentration of hydroxide at equilibrium. Now, considering that we're just told there's no common ion effect here, so we can assume that we start with 0 of the lead and 0 of the hydroxide. This means that we can figure out that the change was plus 0.309 times 10 to the -7th for the hydroxide. And if you know the change in one thing, you can find the change in everything else. So the change in the lead, considering that for every 2 of these, we only get 1 of these, must be half as much. So it's going to be plus 1/2 of that 3.09 times 10 to the -7th, which gets us 1.55 times 10 to the -7th. And on this side, technically it would be minus 1.55 times 10 to the -7th, but we don't care. Minus 1.55 times 10 to the -7th is still, we don't care. Now we have all the information that we need to solve this problem, because we know that Ksp is going to be equal to the concentration of lead 2 plus times the concentration of hydroxide squared at equilibrium. So Ksp is going to be equal to 1.55 times 10 to the -7th times 3.09 times 10 to the -7th squared, which gets us that Ksp is equal to 1.48 times 10 to the -20th, our answer B.